Welcome back, class. Now we're going to look at what you're going to be doing most commonly, which is gram to gram conversions. And first we'll do gram to mole, which is again chapter 6, but typically when you do stoichiometry, you're trying to figure out if you start with grams of this, how many grams of this will you get? Or how many grams, if you need to make so many grams of this, how many grams of this starting material will you need to use? So let's look at one. How many moles of N2O5 dinitrogen pentoxide were used if 210, and they're underlining, they're not supposed to do that, but they're underlining the O to let you know it's 3 significant figures, of nitrogen dioxide were produced. So they're telling you how much product they want to be made, and this is really typical in industry with trying to determine how much of the starting reagent you need. So you're only given one number. You need to start with that one number. And you always need a balanced equation. Again, we don't care about oxygen, so we only ever compare 2 at a time. Just cross off oxygen. Start with what you're given. So always give a unit. We're going to need to put, because we're starting with grams, the molar mass of the NO2 on the bottom. So nitrogen is 14, oxygen is 16, so 16 times 2 plus 14 is 46. And it always goes with 1 mole. Now we're going to go from moles, just like we did in the previous video. We're going to go from moles of NO2, but this time we're going to go to moles of N2O5. We are going to need to use these coefficients. So 4 moles of NO2 will go on the bottom, 2 moles of N2O5 on the top. So that step lets us go from one chemical compound to another, but you always need a balanced equation. Sometimes students ask, how can I determine when I'm doing chapter 6, just gram to mole or mole to gram conversions versus chapter 8? With chapter 8, you always have a balanced equation. With chapter 6, you do not. The units match what they were asking, and we'd stop there. Now normally, in the real world, we take it all the way to grams. So this time we're going to take it all the way to grams, and we're going to start with the O2. That means this time we're going to ignore the NO2. $75 grams of O2. 32 grams of O2 is the molar mass. So you take O at 16 times 2 is 32. And it always goes with 1 mole. Now we're going to use the balanced equation, and we're going to say for every one, because there's nothing here, so for every 1 mole of oxygen will go on the bottom. 2 moles of N2O5 are required. And finally, because they want grams, we're going to have to find the molar mass of N2O5. Nitrogen is 14 times 2, plus oxygen is 16 times 5. 108. So now when we do this, we'd say 75 divided by 32 times 2 times 108. And we started with 3 sig figs, so we're going to end with 3 sig figs. All right, here's another gram to gram conversion. Move this so you can see it a little better. So another gram to gram conversion. Aluminum is an active metal, that means reactive metal, that when placed in hydrochloric acid produces hydrogen gas, remember that's H2, and aluminum chloride. Remember, aluminum has a +3 charge and chloride has a -1, so it's going to be AlCl3. They're going to write it out here in a second. How many grams of aluminum chloride can be produced when 3.45 grams of aluminum are reacted? Now notice they only gave us 1 gram, and that's common. So first write a balanced equation. Make sure my video is not blocking it. There's the equation. We're going to need to balance it. There we go. What you start with, what they want, ignore the other 2. You could actually cross them out if you're doing this on paper or a tablet. Now let's work the problem. Let me lower this a little bit. .45 grams aluminum is what we were starting with. Now, this is the first step always when you do gram to gram. Convert to moles. So you need the molar mass. So we must always convert to moles. Let me move it down so you can see this owl. Video up. Okay. So we're going to find the molar mass of aluminum. It's 26.98. They may round to 27 for every 1 mole. Now we're going to use the mole to mole ratio. 2 moles of aluminum produces 3 moles of ratio. Excuse me. I have to correct myself. We're looking for not H2. I should have canceled it out. We're looking for 2 aluminum chloride. I blocked it with my video. Now use the molar mass. We're going to have to get the molar mass of aluminum chloride. And notice I don't say trichloride because it's a metal. But we're going to have to get the molar mass of aluminum chloride and put that on top so we can get our grams. And aluminum's about 27, chloride's about 35.5 times 3, so 133.3. We started with 3 sig figs. We're going to end with 3 sig figs. And that's grams to grams, so the steps are always convert grams to molar mass, divide. Use the mole to mole ratio from the balanced equation. You're only looking at 2. Make sure you grab the right one. That almost did not. And then convert back to grams using the molar mass of your new compound. So it's molar mass, mole to mole ratio, new molar mass. Units match. All right, this is a little preview of the chapter coming up. Molarity is used for moles. The units of molarity are moles per liters. When working with problems, it is a good idea to change molarity into its units, which are moles over liters. Where I moved my video. So here it is. Here's the unit. You may start to see this on your bottles in lab, which is why I'm doing a little preview. It comes back in chapter 12. So I'm not going to do this one because this comes back in chapter 12. And I'm going to move ahead. Here we go. We're going to try this one. So occasionally when you're doing these, you are given 2 grams or 2 moles, and they want you to find which one's going to run out first. The one that runs out first they call the limiting reactant, and the way that you do that is you have to do 2 equations. So if you're given 2 amounts, 2 equations. And that's actually really common, especially for Chemistry 101. So you're going to have to do an equation for this one, where you start with this, and a separate equation for this one, where you start with this. When you do it, they're wanting to know about O2, so we're going to focus on this. But we would do these one at a time in 2 equations. Again, I would just write 1 here, because we're going to do 1. Hide 1. And I would even hide the KOH, because they're not talking about that right now. So we're starting with the given moles of 1. We're going to have to use the molar coefficients. 3 moles O2. We start with 2 sig figs, so they're underlining 2 sig figs. Now, whichever one gives us the smaller amount is going to tell us our limiting reagent. So we know this one. We don't know the limiting reagent, reactant, until we try the other one. Now we're going to hide the other one. Note that they're taking these numbers, 4 KO2 from here, 3 moles O2 from here, 2 H2O came from here. It's always from the coefficients when you're doing mole to mole. You can always find the limiting reagent just by doing mole to mole. It's just that usually they give you grams, so you have to do at least grams to moles normally. Normally they don't give you moles. So whichever one gives us the smallest moles will tell us our limiting reagent. So this is a bigger number than this one is, and that means that KO2 is going to run out first, even though it's a bigger amount. It all depends on these coefficients. So even though it's a bigger amount, you can't just look at it and go, oh, it's a bigger amount, that's going to be excess. No, you've got to do this mole to mole, at least mole to mole, and you've got to see which one gives the smaller number. The one that gives the smallest number means this is the maximum moles that we could make of O2, which means this one will run out. It doesn't matter that we make more of this. We're going to run out of this first because we're dealing with 2 in the reaction. So our limiting reagent is KO2, or potassium oxide. And then when we talk about theoretical yield, what is a theoretical yield? Hint, that means what's the smallest amount. Sometimes they'll call theoretical yield maximum yield. And it's the same thing. But it's based on what's the smallest amount. So our theoretical or maximum yield is this. It's always the smallest number. The limiting reagent again was the KO2 because it gave us the smallest number. The H2O would be called in excess. Now let's talk about theoretical versus actual. So suppose the theoretical yield, so they're giving it to you, they already calculated it, doing all of this, was calculated to be 19.5. And the experiment was performed, but only 12.53 grams were recovered. You will always recover or produce, they use words like this for your actual yield, recover or produce less than your theoretical because the molecules can't find each other. It just never goes to 100%. So 12.3 grams were recovered, determine the percent yield. Now remember AT&T. It's always actual over theoretical because it's always less than 100. And then anything percent is times 100. So you're going to 63.1%. So they took the actual. Now usually when you're finding the experimental or actual yield, you are doing it in the laboratory. But in the problems, they give it to you. And again, they use words like produces, you recover. They don't usually say this is your actual yield or this was your experimental yield. They say you produce this much product, you recover this much product. So look for those 2 keywords.